Okay. Let's test some sound. Okay, well, I won't echo forever, but okay. Let me put this as a notification. Publish. Yes, yes, good, good. Okay. I don't know why it's unstable. Yeah, whatever. I'll kind of debug that later, but oh my goodness. This cat. Okay, so what are we doing today? We're doing something a little bit different. We're taking a very slight detour from arenas, arenifying everything, and we're gonna focus on one like feature piece essentially. Because I think it's been a little bit too long. We've been focusing on arenas for quite some time. I think it's time to look at something just a little bit different, change up the pace a little bit, and then we'll get back to arenifying everything. Don't you worry. So, what are we doing today? We're kind of taking a look at the TOML format. So if I bring up TOML, this is a configuration language that is meant to be very minimalistic, very easy to parse, very easy to serialize as TOML, and you could transform it into JSON very easily. It has key value pairs. It basically has everything that I would need for configuration or saving state or anything like that for stuff on Fred. And in fact, I use TOML to serialize the configuration stuff. So if you pull up this like configuration and you look at like, let's say background color. So the background color is configurable. So if we go and change this to something like, why is it not changing? Background. Oh, of course, because that's for the file explorer. We're looking at the editor now. I was like, that is not changing. It's very surprising. But if I change like the background color to something like this, right, it looks kind of janky, but you could change it and see like what it looks like. This is all editing like a config file format known as TOML in the background. So we're just kind of serializing all that data to the TOML format. If you look at what this config looks like, it's just TOML, right? There's a hotkey combination for that. So if I look at open config, right, it's Control F9 by default. So if I hit Control F9, it brings up this thing. Otherwise, you could just look at it in the config explorer, which is like the better way of kind of mutating config stuff. But you could also edit the config manually. And for now, at least, this is how you would change stuff like any of the highlighting like key names and stuff like that. So this config format is like very convenient because it's very easy to serialize. It's very easy to even like look at and like make sense of. I can change things very easily in here by hand if I needed to. And I have changed some stuff by hand, like where's the hotkey thing pointing to? Like this is where the hotkeys are loaded from by default, but maybe you don't necessarily want to point it at that file. Maybe you want to point it at something else. So you can go through and manually change this location yourself. and actually the hotkey, I could show you that as well. The hotkey file format is also TOML, and it's extremely simple. It's just this array of tables thing. And we have like the key, the mods, the name, right? And all this stuff is just serialized out as TOML. Now, what needs to change and what's wrong with our TOML handling today? Well, not really anything besides the fact that the TOML parser I'm using and the TOML serializer that I am using is an off-the-shelf library known as TOML, known as TOML CPP or CPP TOML. Actually, let me verify that. It is called TOML++. That's the one, right? So if I kind of like look at TOML++ and I kind of look at let's look at maybe the TOML HPP, right? This thing is kind of a monster. Now let's close the config for now. This thing's kind of a monster, and it's like doing so much more than we actually need it to do, right? Like this, it's 17,000 lines of code, and it pulls in like, let's see how many headers. If I just count the number of hash includes, right? There's one of 40, but maybe not necessarily all these are hash include. Well, maybe they all are, I don't know. Yeah, there's just a ton of stuff in here. There's just so much stuff. So much unnecessary stuff that we do not need. And I kind of want to just get rid of it, right? And parsing TOML is not hard, one. And two, the amount of TOML that we need to parse for what's supported in FRUD right now is so small that I could very easily write a parser in this thing. I could very easily write a parser right now to just make it work, right? So let's kind of explore what that would look like. And I have a really good friend who has written lots and lots and lots and lots of parsers, and he has just this really amazing way of authoring parsers that I think is super easy to understand, and it's very like, it's very intuitive in a lot of ways. So he wrote all kinds of different stuff. And he wrote this, like, I think one of the good projects that you can kind of take a look at, and I can mention it here, is this early parser. So I'll go ahead and link this in the chat. The TOML parser will probably be, it will be like a recursively defined parser, but not necessarily like, I guess it is recursive descent, but it's like the amount of nodes that you descend down to is going to be super narrow. Like you'll probably have a stack of at most 4. But anyway, so this is his early parser, and it's just amazing. Like the amount of work that went into writing this kind of thing is just insane. And I could just do like, I could just keep making this expression like more complex, right? And let's see, what can we do? Let's make it recursive, right? So anyway, you could kind of take a look at this and see like how all the productions how like these productions that he has defined for the language like break down, and how they break down as like a tree. It's super awesome. And in particular, the way that the parser itself is written is just really elegant, right? He has this concept of like a cursor that he uses to track as like sort of this like mini state for the lexer. And then the lexer just like grabs stuff from this cursor, and the cursor is like very friendly to like EOF and stuff like that, because it can issue errors very independently of the rest of the lexer. It's a really flexible design. And he actually ended up writing a TOML parser for one of the projects at work, and that's kind of serving as the inspiration for me to go off and just write, like reauthor a new TOML parser for Fred. And so that's kind of what I've already done, actually. I've done a little bit of the heavy lifting and wrote most of the parser myself. So if I go into my Scratch app here, we can close toml.hpp. So what I've started out here is I've made basically the parser that will emit the necessary information so that like semantics can start taking over, and I could start making sense of like what the parser spit out. So it's kind of broken up like this, right? Like we have this cursor object and a whole bunch of functions that we can invoke on the cursor. So stuff like you can ask the question, hey, is the cursor exhausted, right? You could ask the question, where is the cursor right now? You could ask the cursor, hey, given your input, the entire input that you have, give me the string representation of like some start position and some end position, because the cursor itself is actually what holds the input. The the view of the input. And so that's separated from the actual parser, which gives you like the whole concept of like what is a production and like what are the atoms that I'm building up to create like a larger expression kind of thing. We have like little helper things like the location, so you can query the location of where the cursor is. That's good for diagnostics information. We have various different diagnostics that we can issue. And so I broke it up into this error internal thing, and I'll show you why this is broken up into its own structure a little bit later. We have error data. We have table data. So like now we're getting into the idea of what are we going to end up, like what is the data this parser is going to spit out? So we have like what's a table. And let me bring up like some TOML stuff just to kind of go along with this. So table data, that's essentially what's going to be this right here. So like this is the start of a table. An array of table data is something like this. So this is an array of tables here. So it's really just a table enclosed by these two brackets. It tells the config that, hey, this is a complex object that's also in an array. So in JSON, you might see it as something like this, right? Where you have like an object inside of an array. So if I have like this, right, I can have like multiple objects inside of this array, assuming I actually like delimit it correctly, right? So like here's an object here and here's an object here, and they're all enclosed inside this array. That's what this syntax is capturing, right? Let's go back to the beginning. So that's what the array of table is. Dotted key entry is interesting. So this is the thing that gives you this essentially. So I have a key and then I have another key and they're separated by dot. And the dotted key gives you essentially a list of those things, because I could keep going. Like I could say highlights.foo.bar, something like that. And that's like still a valid table key. So this dotted entry has to handle multiples of those that appear as you're parsing. So you essentially just build up this list of like key parts, which is why this is labeled as a part. And the parse message is the thing that I'm calling, hey, this is the result of the parsing of that specific atom or that production, XYZ, that kind of stuff. We have bare key data, which is literally just the identifier piece right here. That's why it's only a text. That's why it's only a string. We have pair data, which is an XY, like a key value pair. So we have a key here, and then we have a value on the right-hand side separated by equals. So this pair captures that like parse production. So it's the key on the left-hand side and the value on the right-hand side, whatever those happen to be, are captured by these two messages. This is just a float. Floats are captured by the entire floating point expression is captured as the string here. But as you'll note, decimal is a little bit different. And there are some optimizations that we have that we can help the parser influence the semantic engine later. We can help it know like more contextual information so it can more easily parse the decimal that we have. So, for example, I could have something, well, let me actually make the font bigger here. I could have something like 10, and that's just a valid decimal number, and it'd be represented directly as a string like 10, like this. I could also have a hexadecimal value. And so we could represent this as OXFF, like just capture the entire string. But it's better if we, one, emit a specific parse message kind that tells us what the, basically what the radix was of the number, and then we can just capture the number after that point, because we can parse this thing pretty easily. But with like, if we want to turn this into an actual integer value later on, we would have to know, oh, we have to skip like this thing, or like if you have multiple like zeros in front of it or something like that, or if there's like I don't know, if there's all kinds of extra junk in front of it, you kind of want to skip it and just get to this anyway. So what I have the parser doing is I have the parser doing this, where it just snips the OX and it just gives you FF for that decimal data. Similarly, for octal, you can have something like this, right? So we just snip the 0 and tell the parser or we slap a enumeration kind onto the parser message that says, hey, this is an octal number. And so I just have 7 here. And then all we have to do is parse this with the correct radix of 8, and it would just work. And the same thing for binary. Like a binary is like something like this, and that produces like, right, a string with this. So that's kind of a small little optimization path we could take for decimal numbers, depending on what they are. Array values, pretty straightforward, self-explanatory stuff. It's just an array of stuff. And where we have examples of that are like in the tags, right? This is just an array of strings. We have two types of strings. So TOML supports both string literals and just regular quoted strings. The question is, why do you need both? So string literals are really good when you want to have like, you know, I just want to put a whole bunch of stuff in here. I want backslashes. I want like all this stuff, right? Like this, and just have that work. TOML's really good about this because it will preserve literally everything that's in here. However, if it were a string instead, so if I have like this inside of a string, this double quote, that's a different thing, because then all of a sudden these backslash n's turn into the actual new line character. These backslash a might be like I don't know, some kind of control character. There's like backslash b for like bell and all that random crap. Point is, there's a whole bunch of things that those backslashes could mean, and that's why we have string versus string literal. And again, TOML supports both depending on how you start the string. And finally, we have parse message. So here's all the breakdown of stuff I was talking about. So this is what I was talking about, where like decimal can be broken up into these different categories, where we have hexadecimal, we have octal, and we have binary. And so when we encode the parse message with one of these things, that's where we get that special behavior of like snipping basically the prefix of that decimal number and just retaining the integral parts that are needed for actual parsing, or needed for actual like interning of the integral value. And then there's like true, false, array, right? There's some that don't need data, like true and false. These just don't need data, right? It's literally like encoded into the parse message itself. Like stuff like fin, for example, is another one. But you remember how we had error? Error is a kind of a special one. And let me go back up to the error data again. So this is exactly why it's its own struct, is because errors are a little bit complicated. They're rarer than the other parse tree nodes. Or than the other parse messages. And so because of that, you don't want to penalize the size of every other message down here, because some errors like need to encode a whole bunch of information. Some errors don't need to encode a whole bunch of information. But regardless of what that is, you probably only want it to be the size of like one pointer. So when you go to allocate these messages, like you're not allocating more than, you know, one pointer or whatever the largest one is here, right? Like I think it's actually this one, which is 3 pointers. But the point is, the error is like lightweight because it's so rare. And that's why we have this indirection here. And here's essentially just the union of all that nonsense. So we could kind of go through some of the parsing routines, because they're actually pretty interesting. And I think it's sort of useful to understand like why the design of the parser is the way it is, and like why it's so flexible and useful moving forward as we go and take this implementation and move it into Fred. So again, we have like our cursor, we have this messages arena. This is essentially where all those data, those parse messages are going to get allocated onto, and any errors and stuff like that. And then we have this parse atoms thing. The atoms are essentially incomplete pieces of the parse state that are necessary to build up bigger parse states. So, for example, like whenever you have a key and then like a value like true or something like that in TOML, when you parse this thing, you're going to end up parsing the key first, right? And you're going to extract that as a bare key parse message. Now, you don't want to surface that to whoever your consumer is as just the key, because it's not particularly, like, a key is not useful by itself. It only becomes useful in the context of this larger expression. So what we do is we take those little pieces of the expression and store them in the parse atoms list over here. And then once we go to the point where we collect the value, so the value gets parsed independently, and we put that in the parse atoms as well. And eventually we get back up to the full expression, and then we say, hey, full expression, you're a pair. And like, that's the thing that the semantic engine is actually going to care about. So that's why, and at that point, it will go onto the parse messages list. So it'll take these two atoms, combine them, and make a new message that goes inside this thing, and that would be the pair. That's why we have the breakdown of these two things. And then, of course, error messages gets its own queue because it's just kind of easy to test. So if you have any errors, all you need to do is check to see if there's anything on this list. And then the consumer can be like, well, I'm not going to bother I'm not going to bother processing any of these parse messages until after all the errors are gone. So I'm only going to display the errors, for example. Like, that's a choice you can have. Okay, so let's go through probably some of these functions, and then we'll get down to the actual parser. Yeah, let me actually keep that up because it's kind of useful to have as alongside here. So here's just like a couple of helper functions to push various types of errors. Like, these are less meaningful because all they're doing is they're just taking the information and pushing it onto the correct list. But here's like kind of some definitions of like lower level functions, and they do exactly what you would expect, right? They just say, hey, are you an octal digit? Means like 0 to 7. If it's not one of those, it's not octal, right? And then like key, this is essentially like, is this thing an identifier? That's the idea. So processing line feeds is interesting. So shift reduce messages onto the list and then reduce to create the output message. Yes, exactly. Yes, the output message, so that parse message queue gets populated as the result of our reduce. Exactly. There is this concept of the beginning of line, and I can't remember if my friend came up with this or if I did, but I know at some point we added this thing. And this is actually a super useful tool to very quickly calculate the column of a specific line. So whenever you process line feeds, you can have the cursor remember where the index of that line started. And so when you have that, that means that all you need to do to compute the correct column is to take whatever the index is and subtract the beginning of the line value, and boom, you have a column like immediately, which is it's a really nice property, and you get it basically for free if you just process line feeds and remember where the index is. Right. And so obviously when you process a line feed, you also extend the line. So take if. Some of these predicate functions are going to get maybe a little bit complicated, but I'll see if I can walk through them. If anybody has any questions, you can feel free to throw them in the chat. What are some of the types of parse messages? Yeah, let me go through there real quick. So if we look at parse messages, here's all the kinds of parse messages that we can have, right? So we have errors. We have fin, which is like that's the end of input essentially. We have table, array of table, dotted key, bare key, pair, right? All the things you would expect from TOML are going to appear as the parse message kinds. The only thing I don't process yet are dates, and that's because they're damn complicated. Like like parsing a date is like, I don't even know. That's just next level of complicated nonsense that I don't want to deal with right now. I don't have a reason to store a date in TOML yet, and even if I did, I'd probably store it as like a Unix timestamp or something, just to keep it simple. Because the date formats are just so dang complicated. So for the purposes of our TOML parser, I'm not going to support them. Everything else we're going to support, or we're at least going to try. Okay, so let's go through this like very simple take if. The concept of these tiny little functions are to do like a very discrete piece of work and either reject either reject the input or advance the cursor state to some point that we care about. Like all these take underscore things are going to do exactly that. So given some kind of predicate, and this could be anything, for example, it could even be one of these functions, right? So like we could pass one of these functions as input to this take if, and we're going to say, hey, you know, as long as this character meets this predicate, like is octal digit, I'm going to take it or I'm not, essentially. And you return yes or no, you took the input. And same thing for this is going to just eat all of them. So for example, like if I wanted to skip all of the digits, if anything looked like a digit in the input, I could be like, hey, you know, take all of them, right? So this is a combination of take if, so like this is a quick check, and then we have a while loop to actually take everything else after that point, and then we just return true, right? Because we've eaten all the input. The only time this can return false is if what you were expecting to take from the input was not available as the first thing that the cursor was pointing at. Here's take if. This is just a character version of it. It's kind of simpler sometimes to pass like a single character where you don't need like a predicate. So in a lot of cases, for example, like when we're parsing the equals right here, we know we're expecting equals. We don't need a predicate to say that. So we can just, this is essentially like baking the predicate into the function. That's all this is doing. Peak is asking the question, hey, you know, if this character meets whatever the peak or meets whatever the cursor would be pointing at next, like if that thing is equal, then we're going to return true. And then you have like stuff like for eating lines, which is a combination of takes and cursor peaks and stuff like that. Take until, right? This is the point where we're going to be eating a whole bunch of input until we're expecting like a specific character. For example, like if we get to the end of this, and you have like a whole bunch of spaces here, what you want to do is you want to like eat all of the spaces here, and then you want to stop at the equals. So you'd probably call something like take until, where the C equals not space, essentially. Okay. Is this Vulkan OpenGL? This is written in OpenGL or OpenGL. So the reason I chose OpenGL is one, because I already know it, and two, because Vulkan is damn complicated and I don't need the full power of Vulkan. That is really just the shortest answer I can give, but it's the most honest one. Vulkan is just, it has so much power behind it, but like very rarely do I ever need to have access to the level of customization and the level of tweaking that Vulkan has to offer. Most of the time, all I want to do is I want to throw a quad on the screen, right? I don't need to do anything more complicated than that. And usually if I do need to get more complicated, I can reach into shaders and stuff like that to get there. But yeah, anyway, welcome to the stream. Yeah, we're just talking about TOML parsing right now. Require is an interesting one. So require is saying like, I must have this character as input or you get an error, essentially. And this might be a good time to talk about how errors work in the parser. So what you do is, like, whenever you hit an error inside this parser, you just queue an error and then you keep parsing. That's the idea. So we're gonna eat as much of the input as we possibly can and just retain the error states and give you like any other errors that appear later on in the input. And I'll give you an example of that when we start experimenting with what the app does and like how the error recovery works, because those things are kind of useful if like you make a whole bunch of mistakes, like you make a mistake at the top and then you make a mistake at the bottom. Like you probably want to know like both of those locations, right? It's the same thing when you're trying to compile a C program and you're missing like a semicolon here and a semicolon down here and like a semicolon here. You probably want to fix all of those at once. But if you had a parser that only told you the first one, you'd have to fix the first one, then recompile, and then fix the second one, because that would be the next error, and then fix the last one finally after recompiling again. So the idea is like you want to retain as many errors as you possibly can. Require again, this is just the same thing except with like a string literal. This can happen in cases where the parser knows what kind of string it's going to expect. So in the case of like true or false, we know it can only be true or it could only be false. So what we say here is like we want to require that this string is equal to true exactly, otherwise you fail. And that's the idea here. You have to go to bed. Yeah, thanks for hanging out. I also upload these VODs to my YouTube channel, so if you want to check it out after the fact, you can look it up there. Yeah, thank you for the follow. Okay, so that's require. Space, again, a lot of these end up just coming, any of the functions below here just break down into combinations of the functions that we've already mentioned. So like they're just combinations of takes and requires and take whiles and like processing line feeds and stuff like that. So there's like one that's customized for space, or like one for line feeds, one that's going to eat all the line feeds that appear at a certain point, because you can have like a whole bunch of lines like this, and that's totally valid in TOML land. So we just eat all of them at once. CRLF, right? Like if you happen to have a file like this, which is line feed, if you happen to have a CRLF version of a TOML input file, and you happen to have like a line feed that was in incomplete CRLF, for example, it just had \newline and no \r or carriage return, then this would issue like an incomplete CRLF error. Arguably, that might not be a parser error, but it's kind of nice to just know that your input is sort of malformed. So I make it an error. And again, you have like spaces and new lines, right? Like this is essentially the white space eater. This is going to eat all the white space. That doesn't matter. Every parser is going to have this. They're going to name it eat white space. They're going to name it space or new line, right? It's called all kinds of names. You know, it's like folklore in parsers. It goes by all kinds of names, but they all do the same thing. Eat your white space. Okay, so let's talk about some of the parsing routines, right? So for keys, this is what I was talking about where you had like just a regular key like this. So this is an unquoted key. And what we mean by unquoted is it doesn't have stuff like this around it, right? Which actually would be a valid key in TOML. But the point is, like, this just parses exactly this thing and does no more. So it creates the parse atom specifically for that. So we get the cursor to tell us where it is. We take while the key is first, e.g. like isn't an identifier. And then we tell the cursor to snip after that point, and we get the text and place that into our parse message, and then move on to the wherever the next point we're going to call. And you'll notice a lot of these parse routines will return this parse message, and that's so like the larger semantic routines, like I was talking about earlier, where you have key and value as a pair. This return value is what that larger routine ends up using to create the pair object, right? Because we use the result of these little atoms to build up that larger semantic result. Okay, yeah, simple key. Yeah, I kind of have a to-do here. Honestly, I don't use nothing in Fred right now is keying off of keys which might have spaces in them, which is why you would want to have like, so if I have like foo bar equals like 10 or something like that, this is a valid key right now, but nothing I have in Fred is ever going to use spaces like this. I almost always use underlines because of the way that the config object is constructed. I just don't need this flexibility, which is why I'm sort of skipping it right now. I mean, it would be pretty trivial to add, but I just don't need it. And it gets harder too, because like if you have a dot in here, I don't actually know what TOML says about this. If you have a dot there, let's actually bring that up. Let's just do a TOML, a little tiny TOML dive real quick. So if we look at the spec and we look at keys, we can have bare key. This, okay, so if you have dots in here, this is the entire key. I see. So you don't actually process the dots as like a separated, as like a key dot blah or something like that. Now that could be trivial to support, but maybe I'll do it later. Right now we want to focus on actually just trying to integrate something after I'm done explaining a little bit more of this. And then here's regular key. This is the routine which handles that dotted key I was talking about. So essentially, again, it just breaks down to like, hey, do you have a dot following you? And if you do have a dot, then we're going to go into the routine for parsing like the dot key, essentially. And we just do it directly inside the key handler. Because I just didn't see much of a reason to separate this into its own function. It's not that much code, and I kind of just want everything in one place here. But yeah, we have this message that we start. So we create this dotted key, which is really that list. And then we just slowly push entries onto this list, right? We ask the parser to run its key like the key production again to get like another one. And then we just keep going. Boolean true, right? This is where I was talking about where we can require for an exact like string literal value, and then we just pass up the atom. But all this stuff is pretty straightforward. Like the only thing that starts to get interesting is like where we parse integers. Some integers do different things. This is where I was talking about where you could have like the take stuff, like these take helpers, which accept a predicate. Like this is the predicate right here, right? So we're testing the exact like character class. And in this case, the character class is like, hey, it's an octal, or it's like an X digit or a binary digit or something like that. So that's like super helpful to break all these down into tiny little helpers. Yeah, scanning a float can be kind of complicated just because like you can have a dot and then like an E, like an extended float version. Like the exponents can be prefixed with an E and all of that kind of weird stuff. And here's date. I just kind of, say, don't do this. Maybe I should have an actual value for this, but I don't know. Maybe I should have like a not implemented error value or something like that just to handle date, but honestly, I'll just like never support this. It's not a thing. Yeah, so here's where we actually do the breakdown of the different types of the different like radixes of integers that we're scanning. So they're all prefixed with decimal, but like depending on if we scan an X or like an O or like a B, right? It could be a binary. And then we have an extension here to parse octal if it's 0 prefixed. So we just start parsing the octal immediately. Otherwise, it's just like, it's a singular 0, as explained here. No support for hex float literals. Does TOML actually support hex float literals? Let's see. Oh. Let's see if TOML supports hex float literals. Float. Exponents. We can binary 64-bit values. Yeah, you could support NaN and infinity. It doesn't say... So TOML doesn't have support for hex float literals. I mean, you could probably just add that as an extension pretty easily. Yeah, it doesn't say. It would probably say explicitly like we support hex float literals. But honestly, I don't even support this. Like I could probably easily support like infinity, NaN, all that stuff. But it's really just not necessary for any of the data that we're going to be exporting or that we're going to be serializing in Fred. Hi, Frosty Flex. Welcome. Is this a Pratt parser? I honestly am unfamiliar with Pratt parsers. What is a Pratt parser? Top-down parser. But are handling... Well, we don't really have, like... It seems like it's mostly a parser for handling precedence and associativity, but, like, here we don't really have, like, precedence and associativity. Like, we just have very simple, like, key value expression. It's like almost INI parsing with a little bit of flair to it. Which is why this parser is just so dead simple. It's really nice, really simple to read and write. Yeah, I don't know if I would categorize this as a Pratt parser. But welcome nevertheless. I didn't see it was for TOML until you went into the spec. Yeah. Fair enough. Fair enough. Yeah. This is all for TOML. Okay, so there's so we have numbers, we have sign numbers, and then vowels. So like this is the most complicated thing. This is essentially like your general like what's a value kind of thing, right? And here's kind of like the breakdown of how those helpers get dispatched to. Where we have basic string, we have just string literal, and this is with the single quote tick I was talking about earlier, or like the double quote tick. We have array starts. Array is a weird one because it kind of like has this dependency on val, which is like why it's the only function we need to forward declare like this. You have to, because like an array can have values in it, but those values themselves can also be arrays. Like you can have nested arrays and stuff like that. So you have to have like there's like a cyclic dependency between these two things, and that's why it's forward declared. And then later on down here, we have the actual handler for arrays. So you'll notice we just call val here because whatever's inside your array values are just values. That's the only weird one. I think this is the only weird interaction here with the rest of the parser. Otherwise, you can define everything like back to back to back, which is nice. And here's like the three main... So these are the three main things that we actually care about for generating this parse message thing. So this is what you were talking about, Ratchet, earlier with the only recursion in this recursive descent parser. Yeah, it really is the only recursion. It's like that, and then key values is essentially the only place you actually need some amount of recursion. Oh, I changed this thing. go back. Yeah, and what you were saying, Ratchet, earlier is like when you reduce, these are the result of like the reduce operations, right? Like this is where you actually end up getting that full message that something is going to process. And then here's like kind of the top level stuff, right? Like we have an expression. Is it a table of arrays or is it like a pair, right? This is like the main expressional thing that you're going to capture. And then finally, like expression or comment, like obviously you need to account for comments because comments can appear anywhere. Like that you can have a comment like here, right? Or you can have a comment like at the end of a key value pair or something like that. This expression comment thing handles both of them. So this handles the one at the beginning of the line, or this handles the one that happens after an expression has happened. Late night, yeah. It's definitely a late night stream. Yeah. It's I wanted to do something tonight. We had a wedding to get to earlier today, so I had we definitely wanted to partake in that. However, I had this very strong urge to do a little bit of streaming before I went to bed, especially because I had just written this TOML parser and I wanted to try and get some amount of it done, or at least show off some amount of it before we start running with it inside of Fred. Yeah, nice. All right, I'm glad to be here, even if in the background, which is actually where I prefer to have most of my streams anyway. So that's perfect. Yeah, TOML is really nice. Maybe I'll have to show you my TOML parser because this is all like purely from scratch TOML parsing, and it's like super simple to follow. It's probably not RxI simple, but it's simple. Anyway, okay, yeah. So here's expression comment, and then parse inner. So this is gonna do all of the like iterative pieces. So this is gonna iterate through like all of this stuff and capture all of it. Iterate through all of this and capture all of that, right? Like this is the main chunk of parsing. And finally, here's the top level entry point, which is why it's called parser parse, right? This is your main API to get you to start the whole shebang, which is why like the last thing you do is you fin, right? Because you're at the end of the input, presumably. Okay, so let me show you how some of this stuff works, or let me show you. Like, this is just code to print some junk. This is some code to open a TOML file. That's all that stuff does not matter. Like, what does matter is like, let's try and do some stuff. Oh yeah, Frosty. This is this is the instant syntax highlighting is very much a tree sitter thing. Yeah, Tree Sitter is built directly into Fred, and I am super happy that it is because I will use it for all kinds of things beyond just syntax highlighting. But the fact that it highlights syntax instantaneously is super awesome. It's very, very good. Okay. Let me show you test TOML. Let me actually let me do this. So we'll pull this over here. Let me get rid of all this junk. Actually, okay, so this is a copy of the config I have. But this is just local to my repo. So test TOML right here. This thing is just pointing at this test TOML. It's going to serialize it and then just print out all the productions that happen. So let's just try and mess around with it. So if I build app and then build app, I also need to be in the Fred directory like this. So if I run this, okay, so here's like all the stuff. Let's actually go through this in here. So here's all the productions that happened as the result of parsing this TOML file. It's a ton of stuff, but all you need to know is that there were no errors. Because we're going to get down to like a simpler example in just a second here. But the point is, like, it can parse my entire config with no errors. And also, like, I have this little piece right here, these little arrows that show me taking the string value and interning it into like an integral value or a floating point value, and then emitting it back into a string. So I basically, with this, I am proving that I have this bijection where I parse it, I intern it, and then I emit it as serialized text, and then that should basically be equivalent to what I got back. So something like this, like these hexadecimal things. But I'll show you the smaller example because it's a lot easier to read that way. So let's start with something extremely simple. So if I have something like a equals 10, whoops, 10, right? B equals, let's do OXFF, and then C equals, I don't know, some string, something like that. So let's parse this little thing and just see what it looks like. So I've already built the app, so I don't need to do that again. So here we can see a very simple example of what's happening here. So we have a pair of A and a pair of B, right, and a pair of C. The first one's just the decimal, and it's like 10. In this curly brackets here, that's just the captured part of the decimal value, and that's actually more relevant for, or like that's the internalized version of it. So this is actually inside these curly brackets, that's parsed into an integer inside Fred. And then this arrow is what is emitted when I force it back into a string via my formatting function, which is eventually going to be how we serialize back out our data. So I know it's like super dense information, but all you need to know is curly brackets are the actual native variable types, and then the arrow to the string is like serialized to like printf essentially. but it's like stable. So here's like ff. So remember when I was talking about like we can drop this OX and just remember the fact that it was parsed as a hexadecimal? That's exactly what we do here. So we retain this FF piece and we preserved it as a decimal hex. And so when I pass it to the routine that's meant for like turning it into an integer value, all I need to do is I pass it the radix value, which I know because it's hex. So I pass it 16 and it parses to 255 because FF is 255 in decimal value. And then the string is just me turning it back into a string, which is OXFF. Like that's exactly what you expect. And then string literal is just string literal. We could do tables here. So we can do like foo bar baz, and then we can have like C, or like we can have like dd is equal to, let's do like an octal number here. And let's do like a binary number, OB111, something like that. Let's parse this and see what that looks like. Cool. So we have our table, right? We have dotted key, which is a bare key of foo, a bare key of bar, and a bare key of baz, like in order. And that's actually essential for building up these indexed tables later. And then we have our keys, right? Like 63 in octal is 77. And then 1010 in binary is just 10 in decimal. And then we serialize it back to a binary value. Thank you, SDB. By the way, I'm using SDB sprintf to do this stuff. So I get like a lot of stability that way. And then finally, let's actually just do a floating point value. So like FF, we can have something like 3.14159, something like that. Let's just see what that looks like. And hey, what do you know? It parsed as 3.41, basically pi, right? And here's the floating point value internalized, and then here's the stringified value here, right? It all comes out, and it levels out in the end. So let's talk about errors, and then we can start moving some of this stuff into Fred. Okay, so errors. Let's erase all this stuff. So if I have like 10, right, and then I have bar is equal to string. Oh, for floating point, how do you prevent the value from changing when serialized back out. Lots of values won't survive string round trips. That is a very good question. So what I'm doing to do that, or like basically how I'm guaranteeing stability, is that SDB printf has this kind of like stability guarantee built into it, which says, hey, you know, if you serialize a flow in and out of SDB printf, then you're guaranteed to like have this like injective function back and forth, right? Or sorry, like a bijective function back into the float when you serialize it back in. So that might mean you lose a little bit of precision, but honestly, like that precision loss is not super relevant to the amount of stuff that we're going to be doing inside of Fred. Like right now, we don't even serialize any floats in the config, but when we do, because we're going to need to eventually, whenever we serialize like layout information like this, you'll want to serialize like, hey, where was this bar at when you last closed the editor? That kind of stuff, because it's a percentage value, like it's a percentage of what the parent container is. When you serialize that stuff back out, the precision loss there should be totally fine, and you can correct for it when you serialize it back in. So it's not like a huge problem. Okay, so errors. So like, let's say I made a typo here, like J, right? Let's save that and let's see what it looks like. So what happens is you end up having this like errors list that also appears. So we have an unexpected char at like line 1 and then column 10, right? So here we are at line 1. We can see this in Fred, right? Line 1 and column 10. So at that point, it's this thing. Like this is the unexpected character. And that's like super nice because you can have like a whole bunch of these or something like that. 100. Right, and it can point out all of them, right? We have an unknown char at 26. I think some of these columns might need to be adjusted. Yeah, some of these columns need to be adjusted. Anyway, I have like okay, so there's clearly some bugs in the locations of these things. I think it's because the parser actually isn't. I think the parser actually isn't processing new lines whenever it has an unexpected character, which is fine. Like I could fix that later though, because errors are not going to be super rare. The point is like the very first one is super accurate. That's what you need to know. Let's check chat. Yeah, that's what hex floats can be used for sure. And I think that SDB true to, or does the SDB lib handle hex floats? Yeah, they do handle hex floats. Right. Yeah, I mean, you could totally do that. I think probably when I get there, maybe I'll extend the parser support to accept hex floats and make that work. Let's see that float algorithm. Yeah. Yeah, the round trip proof is really nice. But yeah, hex floats should be pretty trivial to add. But the point is, I think we might be ready to try and integrate some of this into Fred. And I think the first thing we're going to do is we're going to need a little library to handle all of this stuff. So for the parser, so what we're going to do is we're going to split this out into a header that has tiny TOML inside of it, and then a CPP file that has the implementation of the parser. This way I can reuse it across multiple components, because right now we have hotkeys, which needs TOML support, And then we have config, which needs TOML support. So both of these things are going to end up getting, we'll need access to that specific parser. Yeah. Okay, so let's start getting on that stuff for now. Basically, how I start this is I just start it by copying one of these headers. Control-Shift-S. And we're going to call this, let's just call it TOML parser, or actually, Tiny TOML, which is in honor of my friend who actually named it this. I think it's just kind of a cute name, Tiny TOML. Okay, we're gonna start ripping out stuff from this. So what do we actually need? What do we need from this? Let's just copy everything and just rip out what we don't need. It turns out we don't need like most of it. Yeah, we don't need like most of this here. I think we just need the parser. Yeah, we don't even need message to string. Yeah, we need parse message. Do we need parse message list? I think we're going to need most of that. Let's get rid of all this. We don't need this. We're going to need that. All this stuff we're going to need because those are defining all the core data structures. We're going to need error. Do we need locus here? Yeah, TTH. Yep. That is actually not a bad name either. Or naming the header that. Add Tiny TOML. I like it regardless. It's good. Column. Do I want locus here? Yeah, because whoever's consuming it will probably want to print whatever the heck the error is. We definitely don't need any of this. We do unfortunately need the cursor definition because it goes inside the parser, which is down here. Yeah. Okay, we need some stuff. We also need red strings. What else do we need here? I don't think we need any other types. Yeah, it should be all we need. Okay. And so over here, Tiny TOML.cpp. Delete all this. So if you don't know how I organize my headers, my main is a really good example of this. So this is something I learned after working on a project called O'Reilly. O'Reilly was a database back in 2014 that was like a key value store, but it was like a distributed database. It was a really cool project, actually. But I learned a really important lesson about how to organize your headers for kind of just hygiene moving forward. So essentially, the idea is that you have your C standard library headers come first, and then your C++ C standard libraries are next. And then finally, your C++ standard library headers are next. And then finally, you can get into all of your headers. And then you go into third-party code and then platform code. And that ordering has actually served me very, very well. The other thing, too, is that for files like this, or like I'll actually go pull up Manager again. For files which are implementations of header files, that is the file that goes very, very first. and then you resume the order that I described earlier. That ordering has really helped me kind of get a hold of like where my headers are going and like where my symbols are coming from and all that good stuff. And I use it all the time. Anyway, little piece of history there. So let's go back to Tiny TOML. Let's put it over here, and we're gonna grab we're gonna grab like the whole parser. We're gonna grab the whole parser again, essentially. Except we're gonna be cutting stuff out this time. So let's paste it all in here. So we don't need this. We don't need that. We want make cursor. So I'm essentially going to describe, or I'm going to define what the public interface looks like based on like based on what I need to actually pull out and expose from here. Cursor is defined elsewhere. Right, we said these are going to be defined out there, as is locus. All this stuff does not need to be defined here. Takes notes. What does the specific ordering get you? Mine is similar, but some groups are in other places. So the reason you want the ordering that way are because essentially it breaks down to you don't want platform code. You want to reduce the amount of area that your platform code is kind of like mangling with standard library headers in particular, and or your own library headers that happen to be commingled with that stuff. So it honestly just comes down to reducing the blast radius of what the heck the third-party libraries are doing. Because the thing you can always guarantee is that the C let me actually go back down here in like the C standard library headers are the most stable thing you can possibly imagine on your system. Like those basically can never change. If they change, the entire world breaks. So these are always safe to put first. And with these C++ library headers, they're a little bit more, they change a little bit more frequently, but because they're distributed with your compiler, you can generally count on them to be like very stable. They won't inject a whole bunch of extra junk into your code. And stuff like you don't have to worry about macros polluting things and stuff like that. So if I were to include like windows.h up here, that is just going to be all kinds of hell's gonna break loose if I include standard library headers after that thing. Because, for example, the Windows header is notorious for creating the macros like min and max, and depending on what standard library you're using, it may not protect against that kind of thing. So, yeah, the standard library headers are always good to include after that. And then, of course, all the headers that you have direct control of are extremely good, or like you know how well behaved those are, so those are good to include after that. And then of course your platform code and your third-party code come after that. That's basically how that breaks down. Hopefully that answers the question. Okay, let's back to destroying more of this stuff that we don't need. I think I want to keep this function for now, because I may want to use it later. Let's go delete all of this junk. Oh yeah, the same thing for that function. We want to keep that around. Yeah, we definitely want to keep that around. Okay, let's keep going down. Oop. Parser. This. Okay, make parser. This needs to be exposed for sure. So let's go back up here. I like to define all the structures first and then define the functions last. I think that's kind of a useful way of doing it. So we can have make parser, and then I will also take this function, this one here. Then I like creating little headers for things like parser creation, parser entry. I know it's not there yet, but it will be. And then helpers, something like that. I might have converted you. Well, I'm glad. It's worked really super well for me. You know, you don't have to use the advice, but it honestly has saved me from some really annoying problems with integrating third-party code in particular. Parser Atom. So we have make parser, and then we eventually want the very bottom function down here. Print message. We want this parser parse. This thing. Cool. So here's basically the minimal amount of work necessary to make this parser work. So let's see if I can rely on this and try and build our app again. So all I need to do is do like if zero all this stuff out, end if, and then I can include tinytoml.h there. Yeah, let's move it up because it needs, that's how it's sorted. Okay. Oops. That's not sorted. There we go. So if I do build app, will that work? No, it does not. Print message is not a member of tinytoml. Okay. Yeah, it's because the printing routines are not there, but I can kind of expose those. Do I want to expose these? Or do I just want these to be kind of part of the app? I think I can make these just part of the app and just pull them out of here. Yeah, let's just make them in here. I think that's probably just the easiest way of handling it. I have those there. Will this build now? Sorry to keep bike shedding. I normally do local headers first, forces them to include or forward declare what they need and not accidentally rely on them being transitively included. Yeah, that's definitely a way you can solve that problem. Yeah, so my method is like, it's very useful when you have a little bit more hygiene over your headers. But yeah, you can run into this problem where you have like accidental dependencies on like std vector where you didn't include vector before. But honestly, I think that problem is also solvable if you just try to compile your headers in isolation, like literally just run the compiler over them and see what happens. That's a good way of figuring out if your headers are self-contained or not. But in a lot of those cases, like for a handmade project, I would pretty much not care. But if I'm working on a team, I'd probably do something like make sure that my headers are more self-contained by compiling them in isolation. That's why an implementation file includes its header first. Yes. Yes, exactly. Like that's exactly, or that's a huge reason why you do that's a huge reason why you do this right here. Exactly what Ratchet brought up. And then it's like much harder for those files to just like implicitly depend on things. And then the only cases where you actually get that behavior are these like standalone header only things where like maybe you should question whether or not those need to be header only things anyway, and like maybe they should just move to implementation or something like that. Or maybe they're just a bunch of type defs and you don't care. But yeah, this really massively mitigates that issue. Okay, what was I missing over here? Error kind, string not found. Okay, I guess I maybe should expose these because these will be helpful no matter where I am. So let's just copy these. So helpers, right? Let's just have those there. This should build now. Okay, cool. Build app, right? We still get our thing. Let's actually fix that real quick. Make sure we can get a valid parse. Cool. Okay, we still parse. So that means our header is actually working, which is super awesome. And I did actually run into this problem where I am depending on Arena here. So like I need Arena now because I have this right here, make parser. And it didn't yell at me before because inside of here, or like because strings actually already included Arena. Fred strings already included Arena. Cool. Yeah, I'll definitely try it out, see how it works out for you. Okay, so inside the app, I can actually delete all this code because I don't no longer need it. And now app is significantly smaller, which is nice. It's a good place to be. Let's start by checking in all this code. So we have get add source, get add inc. And then the only difference in here is like the deletion of all the code, right? Cool. That's what I expect. Move TOML parser into its own file. So now we have the basis of our TOML parser that we can start replacing all of the nonsense with, all the nonsense C++ stuff with, and get something that's like actually way better, and we have way more control over, and it's just as performant, if not more so, than the off-the-shelf thing. Unfortunately, it got to be a lot later than I expected it to be. What was I using before? I was using, or I still am using, config. So I'm using TOML++, which is a off-the-shelf. Actually, I can pull it up over here. So if I look at TOML++, here's the thing. I mean, it's a fine library, I guess, if you need like an industrial strength kind of TOML parser. But we just don't need like the level of configuration and like the flexibility and all this stuff that this TOML parser offers. Like, and it just builds up like std map and all this other nonsense that you don't have control over the allocations of. It's just crazy. I just got bit by header only modern C++ libraries never again. Yeah, exactly. It's just they're just kind of a nightmare to deal with nowadays. And like the fact that the library is header only is becoming more and more, it's becoming less and less of a feature and more of a like a maintenance burden. Because then you have to just deal with the implementation living all over the place. And your compile times are just suffering and dying as a result. Let me actually give you a motivating example as to why I actually want to do this in the first place. So, in Fred, so I have these two cases where I have config and I have hotkeys, which both use the TOML parser here. just to kind of get like a back of the napkin if I didn't have, like, let's just say I didn't have any of this parsing stuff, because like the implementation of these files is super straightforward. Like they're super simple files for the most part, in terms of like what I'm pulling out of the TOML. So most of the compile time is going into the TOML itself. So let's see what happens if I like if zero out. Well, let's not if zero them out first, because you want to see like what it looks like with it first. Okay, so let me enable these again. So there's that, and then there's this. Or actually, I need to modify the build script. Okay, so there's this handy flag you can pass the MSVC compiler. Nukes debug performance suit. Yeah, exactly. Like you have to rely on so much freaking inlining for it to perform correctly, or like perform with any degree of like debuggability. Yeah, it's just a pain. Anyway, there's this flag you can pass the compiler, which is BT plus. It shows you like how long the compiler took. So I have this build mode in Fred, which tells me that, or which instructs the build to only compile the editor. So you can see right now we take about 3.5 seconds, right? Let's do it a couple of times just so we can get an idea of what it looks like. 3.5 seconds, right? Yada, yada, yada. And that's just to compile the Unity file, which is, to be fair, that's all of Fred. Like, that's literally everything in the editor, which is fine. So, like, this is how long it takes to build the entire editor. Without optimizations, mind you. Don't forget to add the TOML++ to the separate sources list. TOML CPP. Well, actually, it's all in the implementation. So like in my main, I don't even have like toml.cpp. I just build it as a header only library. But just for kicks, right? So like that was about 3.5 seconds. If I got rid of this library here, in both places, because you have to get rid of it in both places, otherwise it'd be included in one of them. Let's see what the compile times look like. Right? So it's already like almost a second faster just by getting rid of those things. We're at 2.7 seconds to build the entire editor. That, again, that's literally everything. It's still kind of slow, and I'm still going to remove some stuff to trim off that fat. But the fact that you get rid of like that one dependency and you get like almost a whole second of compile time back it's just upsetting. So it needs to go away. It needs to die, and I can't get rid of it fast enough. Yeah, it's just obscene. So anyway, I was just compiling Fred a couple of times yesterday, and I just kept hitting this like, why is it so freaking slow? And I just did a benchmark analysis and figured out it was just all the crap that toml.hpp is pulling in. It just pulls in so many headers. It pulls in like almost every single STL header to build this thing as a header-only library, which is its default mode, by the way. You have to go out of your way to make it as a separately compiled thing. But yes, I want to get that second back. And this TOML parser that we just wrote, it compiles in like 0 time flat. Like let's actually just do that real quick. I can show you how long it takes to build that thing, so we can get a back of the napkin for that. Let's add BT plus. Oops, why is it ignored? Here we go. BT plus. Right, so like it builds in 0.8 seconds. Like that's with the whole TOML parser and the vast majority of the code that is going to be starting up Fred, like 0.8 seconds, like not bad at all. I could live with that compile time. Okay. Anyway, so let's get back to this. Is that what it looked like? Yes. And then this thing. Oops. Yes, I do want to save. Anyway, exactly. Yeah, and Abner, you're just in so much of a better position because your whole thing is already in C, and C just compiles blazingly fast. Like I would move to C, but there's just so many things about C++ that I enjoy. I mean, the times when you need templates and you just can't, like, a macro just isn't cutting it, or they're few and far between, but when you do really need it, it's just so nice to have access to something like that. It's a trap. I don't disagree with you there. But anyway, yeah, I think that's probably going to be all I'm going to be able to do tonight. It is a little bit later than I anticipated, but I think we got a lot of work done. We ended up at least factoring it out into its own header, and proving out what we wanted to prove out with the parser, walking through the implementation of it, so we got like a good kind of description of how that thing is going to work. And now the next piece is just integrating, which should be fairly straightforward, honestly. It's just a matter of iterating the parse messages, assuming there were no errors, and then building up the semantics of it. I think the first thing we're going to tackle is this hotkeys, because it's super simple, right? It's literally just an array, like an array of tables, because there's no other types of tables in this hotkey list, with a couple of strings, and some of them have mods, like for example control, right? Like control shift, right? It's just a comma, like it's an array of strings. Like this is as simple as you could possibly get. What about Clang extensions? Some modernity right there. Yeah, there's some of them. If only you could figure out how to make it so that compiling in C++ mode, no changes, and 50% slower. Yeah. Unfortunately, the way that C++ has been trending, it's only going to get slower. And the thing is, like, if you look at language mode or language additions from C++ 98 to C++ 11, the way that they change the language forces the compiler into disambiguation modes that it never had to do before. And that actually introduces like a lot more scenarios where the compiler has to backtrack and actually try and reparse certain things. The most notorious of which are, if you're unfamiliar with them, are the deduction guides, right? They took one of the most ambiguous function declaration like things in all of C++, and they extended it and made it a template. Like, it's just, I don't know who made that decision, but it is baffling to me because it really screws up the heuristics of how the parser is supposed to work. So if you want faster C++, like at a bare minimum, just compile with like C++ 11 this way, because that was introduced in C++ 17. If you could compile without C++ 17, you'll probably have just a faster parser. Like a faster C++ parse in general. But I like to I'm at least enjoying C++ 20 because stuff like concepts are kind of nice. The fact that you can constrain functions with things that are actually meaningful is a very useful aspect of concepts to me, and I think like that's a genuinely good addition to the template system. Yeah, how awful. Yeah, deduction guides. It's just awful. It's terrible. Okay. Anyway, I've rambled for a little bit too long. I appreciate everybody showing up tonight. You guys are awesome. we'll do some more TOML parsing stuff probably tomorrow. Maybe not tomorrow. I don't know. It's Halloween. We'll see. I'll definitely do some this weekend, though. We'll get something in there. Anyway, thanks again, everybody, and I will see you next time. Bye.